In this statistics section, we will be discussing measures of relative standing and adding a new graph to that collection. We're going to add a box plot. So this section talks about looking at how numbers compare to each other within our data sets. The most important concept that we're going to discuss in here is the z-score. We are going to use the z-score throughout statistics. So very important that you understand what a z-score is and how to calculate it. We'll also discuss things like percentiles and quartiles, and those quartiles are what's going to give rise to the box plot that we're going to learn how to graph. So let's get started. First, let's start with z-scores. A z-score is sometimes called a standardized score or a standard score. Your z-score is just a number of standard deviations that any value is above or below the mean. So if you're above the mean, your z-score is going to be positive. If you're below the mean, your z-score is going to be negative. And all you have to do to find your z-score is just take that data value, subtract the mean, whatever that difference is, divide it by the standard deviation. And that will tell you your z-score. Z-scores are always rounded to 2 decimal places. A lot of the time we're going to be using charts to do stuff, and z-scores are always 2 decimal places. So z-scores, 2 decimal places. Some important properties of our z-score. Our z-score is always going to be a number, and it's always going to be that number of standard deviations above or below. Above is positive, below is negative. It has no units of measure. Number 2, no units of measure. It's just a number. And we would call this data value, this z-score, significantly low if z is below -2. If it's above +2, we would call it significantly high, because that means we are more than 2 standard deviations away from the mean. And make sure that, and again, just number 4 is just a recap. If your data value is below the mean, your z-score must be negative. So if you calculate it and it's not negative, you've done something terribly wrong. So make sure that you're paying attention to where your data value is compared to the mean. All right, so I have an example here. So in the first example, we're talking about adult body temperature. So which of these 2 situations is the most extreme? And that's where the z-score is going to come in, so we can compare very quickly. So we've got this first situation where the temperature of an adult is 99, and they gave us the information where that came from and what the mean is and what the sample standard deviation is for that. So if we want to find the z-score of this particular person who has a temperature of 99, their z-score is going to be equal to, okay, the data point, the data value that we're looking at, minus the mean divided by the standard deviation. Always the same. Okay, we plug that in to our calculator. I would do a little division there, and then divide by 0.62, and I get 1.29. So we have a z-score of positive 1.29, which tells us that we are 1 1/4 and then a little bit more standard deviations above the mean for this particular person. Now let's go look at the situation about the weight of a quarter. Again, it gives us all the information we need, talks about how many quarters, talks about the sample mean, talks about the standard deviation. So we can calculate the z-score for this particular quarter. So again, the particular data point we're talking about minus the mean divided by the standard deviation. Notice exactly the same formula. We're just plugging in different numbers. Okay, put that in my calculator. Do the difference first, whatever that number is, divide it by the standard deviation, and I get 2.26. Notice, also positive, so we are also above. But notice, we are more than 2 standard deviations above the mean. That means this is significant. And if you compare those 2 numbers, 2.26 is much higher than 1.29. Therefore, the situation with the quarter is more extreme because it is farther away from the mean than the temperature of the adult data that was given to us. Okay, so please remember that when you're looking at z-scores, anything above a +2 or below a -2 is a significant value. Any data point that is within 2 standard deviations of the mean on either side, above or below, is considered not significant. You'd just be the lonely average, people. Sorry. All right, so here's an example. If there's an earthquake, and it says one of the stronger earthquakes has a magnitude of 4.01. And again, you don't have to know anything about the Richter scale or how it works or whatever. So if we have an earthquake that's 4.01 on the Richter scale, would that be considered significantly high? I don't know, but I do know I can find its z-score. and then I can find out how many standard deviations it is from the mean, and then I'll know if it's significant or not. So let's calculate its z-score. So we have an earthquake of 4.01. In the data, we can find out that the mean is right here, so minus the mean, which is 2.572, and then we're going to divide that by the standard deviation for our earthquakes, which is 0.651. So again, same thing we've used. All right, so do the difference first, whatever that number is, divided by 0.651, and I get 2.21. Okay, so is it significant? Absolutely. The answer is yes, it is high. It is significantly high. Significantly high. Why? Okay, because my z-score is higher than 2 standard deviations above the mean. And that's the because part is the very important thing that you have to be able to verbalize when we're talking about data. Why? Not just is it significant, but why? It's significant because it is more than 2 standard deviations above the mean. So even though a 4 doesn't seem very high, you know, they have those ones in California that are like 7s and 8s. So just note 4 is statistically significant. Okay, so that's z-scores. So get used to working with them. You're going to see them a lot in a statistics class. Right. Another thing that we can use to talk about relative location is percentiles. And you've probably heard of these, you know, like when you're a baby and your mom brings you to the doctor and get all your checkups, that tell you like, oh, he's in the 20th percentile for weight, but the 80th percentile for height, which means you're just kind of skinny, but you're kind of tall for your age. Doesn't say anything about what's going to happen later on. Who knows? When I was a kid, I was tiny, but you know, all of a sudden in the 4th grade, I grew like 1.5 feet. It's crazy. So just realize that percentiles are just meant to be, you know, generalized locations from where you are compared to everyone on the planet. So if you are finding a percentile, all you have to do is to find the value of that data point for whatever percentile you're looking for, is you want the number of values less than you. Divide that by the total number of values and multiply it by 100. Again, percent, you want to multiply by 100. But that's the important part of that numerator. Make sure that you're counting the number of values that are below you. That's very important. All right, so let me give you an example of how you can find a percentile. So let's say we have this data set of the 50 wait times at Space Mountain. So a much larger set than we've worked with in previous examples. Same ride, but much more data this time. Find the percentile for the wait time of 45 minutes. Okay, so luckily these data values are all in order and there's 10 per row, which makes it nice. 45 is right here. So here's the data we want. So if we're finding the percentile, okay, that's equal to, remember, the number of data values below where you are. So I've got 10, I've got 20, I've got 30, and then 31, 32, 33, 34, 35, 36. I have 36 data values below me. I am 45. Okay, divided by the 50, and then you're going to multiply by 100 because you want it to be a percent. So 36 divided by 50, then multiply by 100, and you get 72. So that means that the 45-minute waiting person is what we would call P sub 72 is equal to 45 minutes. Like that sub 72 tells you the percentile. The 72nd percentile would be 45. Okay, so that just means that there are 28% of the people who've been waiting longer than you. That's all it means. 72% of the people have been waiting less than you. So it just kind of puts you in perspective. And if you think about it, notice the bulk of the people are below you and there's only these people in front of you. So it kind of makes sense. So that will help you. There's some notation we need to talk about when it comes to percentages. N, of course, is still the number of data values in the set. That's the same. K can be used as well. So rather than using the P sub, right, we use this one, right? We use the P sub K, right? P sub 25 is the 25th percentile. You can just use K as your percentile. So you can just say K equals 25. That if you say K equals 25, that is exactly the same thing as saying P sub 25. Those are exactly the same thing, just different ways to represent it. And different textbooks will use different things. There is something called a locator, L, that talks about your position in the list. So if you're the 12th value, then you are L equal to 12. And a lot of times they may ask you to locate, like they may tell you, you're in the 36th percentile, find the locator of this, data, this 40 data set, or something. They might ask that. So if that happens, I have your textbook, which is lovely, has this nice little flow chart that you can kind of follow, which just says here you start, you sort your data. Obviously, you want to go from lowest to highest. You start computing, right? You can compute the locator. You can compute the number of values. You can compute your percentile. If your locator is a whole number, because sometimes that won't come out perfectly. So if your locator is a whole number, then you want to make sure that you find your piece of k by adding the nth value and the next value and then dividing by 2. So you take that number plus the one above it and divide by 2. But if you don't get a nice pretty whole number, it's pretty easy. You're just going to change L by rounding it up to the next bigger number. That's it. So I like this little flow chart because it kind of walks you through it. So if you ever get lost, just come back to this flow chart and it'll walk you through step by step what you need to do. All right, so let's do one of those. So we've got these 50 people again. I would like you to find the value of the 25th percentile. So again, I'm asking you for the locator. So the locator, I'm going to start with that formula. Okay, what is my k? My k is my percentile, and they told me that was 25. So 25 over 100 times n, which is the number of points in our data set. All right, so that's 50. All right, so if I do that all out, that's 1/4. 1/4 times 50 is 12.5. So my locator did not come out to a nice whole pretty number. So that means I'm going to round it up. So we're going to round up to the 13th position. All right, so let's go to our chart. Let's find our 13th position. So that's 10, 11, 12, 13. Our 13th position is right here. So what is the 25th percentile? That is 25 minutes of waiting. Puts you in the 25th percentile. So hopefully that example walks you through. All right, another thing you can work with other than percentiles are what are called quartiles, where we only look for the 25th. So just so you know, quartile 1 is just the 25th percentile. Quartile 2, that is your 50th percentile. Quartile 3 is your 75th percentile, and quartile 4 is you're at 100%. So this is your maximum value here. If you're at 50%, that's your median, right? You're halfway. So I find quartiles very helpful because they kind of chop my data into these 25% blocks. So I can see what's going on. But just please take notice that there isn't this universal agreement on exactly how we do this. Some books say one thing, other books say another thing, depends on the author. So just make sure that you pay careful attention to whatever textbook and author you're using, because they may use slightly different things than I'm going to use. So just, again, it's just one of those things that, it's style, and those change over time. There are lots of things that we can do with the quartiles and percentiles. We can find what's called an interquartile range, which is just Q3 minus Q1. And don't worry, we're going to walk through some of these. A semi-interquartile range with this Q3 minus Q1 and then divided by 2. You might find the mid-quartile, which is Q3 plus Q1 divided by 2. And again, these are all just things that we can do with our quartiles. There's something called the 10 to 90 percentile range, which is just the majority of people. Like you've got the lowest 10%, which are like, the end that we're worried about, but we're also worried about the upper 10%. Like if we're talking about weight, if you're in the 10 to 90, you're pretty much normal. That's pretty much everybody. But you've got that 10% on the bottom that's really, really, really thin. And then you've got that 10% at the top that are really, really, really obese. And those are the people that, need the most help, from a health perspective. So that's who they're going to focus on. But the rest of us, we're all in the middle. They kind of leave us alone for the most part, other than, the doctor may be saying, hey, maybe you should gain some weight. Hey, maybe you should lose a little weight. For health purposes, but that's kind of what the percentile, that 10 to 90 percentile is used for. But for us, when we're talking about all this quartile stuff, we're really going to focus on what's called a 5-number summary. And that 5-number summary consists of just 5 values, hence the reason they call it a 5-number summary. Remember, math people, we are not very creative. Number 1, we look at for the minimum. Number 2, we look for the first quartile. We find that Q1. which is the median of the lower half of the data. And we'll talk about how to actually find it in a second. The third number we're going to need is the second quartile, which is Q2. That is the median of our data. The fourth number is the third quartile, Q3, which is the median of the upper half of the data. And that fifth number is the maximum. All right, so I have an example. We're going to walk through how to find this 5-number summary and then talk about how we can use it. All right, so here's our Space Mountain times again. I know you guys are probably getting sick of these, but we're going to go through it again. We're going to find our 5-number summary. All right, number 1, we are going to find our minimum value, and that's probably the easiest, right? That's 10. So that's 10 minutes is our minimum value. All right, we also need to find our maximum. That's number 5. So I'm going to find that one next because that's kind of the easiest. So that's the maximum, and that is 110 minutes. So I usually start with those two. I then go to Q3. Oh, Q2, sorry, Q2. Q2 is the median. So I always do that one next because I think that's the easiest. So there are 50, which means that there are going to be 25 on the low end and 25 on the high end. So 10, 20, 1, 2, 3, 4, 5. So the median is actually right here, which means I'd have to find the mean of those two numbers, but they happen to be the same thing, luckily for me. So that means the median is 35 minutes. So there is my Q2. Okay, now I need to find my Q1. So Q1 is the median of the lower half. So we're just looking at this to here, right? These lower 25. There will be a number in the middle because there's 25 numbers. There's going to be 12, and then there's going to be 1 in the middle, and then 12 at the top. So I'm going to count 10, 11, 12. There's my 1 in the middle, and then there should be 12 above it. Okay, so there's my Q1, 25 minutes. It is the median of the lower half of the data. And then I'm going to do the same thing. Number 4 is my Q3, and that is the median of the upper half. So do the same thing. I'm going to count up 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There is my Q3, and then there should be 12 above. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Perfect. So 50 minutes is my Q3. All right, so that is how you find your 5-number summary, which honestly, it's just finding a bunch of medians, so I like it. Not too difficult. Okay. From this 5-number summary, we can create what is called a box and whisker plot, or sometimes people call it just a box plot. Again, it just depends on the textbook you use. This is just a data set because it's going to break it into those 4 quadrants, those 4 quartiles, the 25th percentile, the 50th, the 75th, and the 100th. And it's going to put it in a visual format. So the procedure for doing this is you have to have your 5-number summary. That's where you're going to start. Then you're going to construct a number line, and that's where it's going to work. And I'm going to show you how to label everything on this box and whisker plot. But the box part is from Q1 to Q3. You're going to make a box from Q1 to Q3, and then the whiskers are going to come from Q1 down to the minimum and from Q3 up to the maximum. So those are going to be the whiskers on the end. So let me show you. All right, so you may need to look at the data that we talked about because that 5-number summary we wrote down before. So I'm going to recap it real quick just so you know. So we had the minimum, which was 10. We had the Q1, which was 25. We had the Q2, which was 35. We had the Q3, which was 50, and our maximum, which was 110. Okay, so that was our 5-number summary that we calculated earlier. Okay, so what you're going to do is you're going to label your number line. And I picked this number line on purpose because it's going to perfectly fit. So every 10 minutes, that's going to be a tick mark on here. 90, 100, 110. I picked this on purpose because I knew it would work. Okay, so what you're going to do is you're going to create a box around this data. So at 25, we're going to put a line. At 35, we're going to put a line. And at 50, we're going to put a line. And we're going to construct a box. So that box right there is the inner 50% around the median. And notice, here's my median right here. I've got a little bit more data than I do here. So this 25% is a little bit more spread out than this 25%. And that's important that we realize that. All right, then we're going to put our whiskers on. So our minimum is 10. I'm going to put a dot, and then I'm just going to connect that dot. There's the whisker on the low end, and then do the same thing for the maximum. Dot, and then a whisker for the high end. And notice, these whiskers also represent 25%. And notice the whisker on the low end is much smaller than the whisker on the high end. That means that that top 25% of people who've been waiting in line is much more spread out than any of the other 25th percentiles that are here. So this tells you a lot about the spread of your variation. I mean, the variation of your data and how spread out it is compared to the rest of it. And when we talk about that, that's called skewness. So let's talk about skewness a little bit. So I have some histograms, and then I have their corresponding box plots directly underneath them so you can see. So notice how in a normal distribution, look at how pretty this is, right? Everything's kind of spread out. This is a little bit smaller than this one, but like neither of the whiskers is really long. None of the boxes is significantly longer. You know, it's all spread out. But look at the skew over here. We've got a skew this way. Look at where everything's down here, and then we've got this really long whisker. And then if we've got uniform, look at how everything is really kind of how that stretched out that box is compared to the normal. So these box plots can just give you a representation as well as what the data is, how the distribution looks, which I think is really kind of cool that we can get to that. I have another picture here, which also like I have the histograms, but I also have the Q1, the Q2, and the Q3 labeled, and then compare it to their box plots underneath. So that's another great way that you can look at it. The important thing that you need to know is that box plots do not show the mode. So if you look at mode here, like it has two modes, but then you look at the box plot, that doesn't really, there's no really correspondence between there. So just know that box plots are not very good at showing mode. So keep that in mind. There is something that you can do called a modified box plot. And let's talk about that for a little bit. If you were going to do a modified box plot, what that means is that you're not going to take into consideration those outliers. So we have to have a process of how we identify what an outlier is. So in order to do that, we need Q1, Q2, and Q3. Okay, so the first thing you're going to do is you're going to, after you've identified Q1, Q2, and Q3, is you're going to find the interquartile range, which is just Q3 minus Q1. Find that range, and you're going to multiply it by 1.5. Okay, so if a data value has Q3 plus that, what we found in step 3, add those together. If that's greater, any data value that's greater than that is going to be an outlier. Do the same thing with Q1. Take Q1 and subtract that 1.5 times the IQR. If you have any data values lower than that, then those will be outliers. All right, so first we're going to find some of those things, and then we're going to actually talk about them. So those modified box plots, again, it's the same box plot, but anytime you have an outlier, you're going to put an asterisk, so you know that, hey, this is an outlier, this is an outlier. And rather than going to that maximum or that minimum value, you're going to stop at the data value that is not an outlier. So your whisker is going to end at the last data point that's not considered an outlier. So let's talk about that Space Mountain one we just did, and then we'll go back to it, right? And I'll talk about how we can fix it. So we've got our Q1, Q2, and Q3. Let's first calculate our IQR. So our IQR, remember, is just Q3 minus Q1. So 50 minus 25 is 25. And then you're going to take 1.5 times that IQR. So 1.5 times 25 is going to give you 37.5. Okay, so we are going to take Q3 plus that 37.5. So our Q3 was 50, so 50 plus that would be 87.5. So that means anything higher than 87.5 is going to be an outlier. And then you're going to do Q1 minus 37.5. Well, our Q1 was 25, and 25 minus that would give us a negative number. And obviously you can't have a negative number of wait times when it comes to a ride, right? So that means we already know right now there are no low outliers. Okay, on the low end, we are not going to have any outliers, but we're going to have some on the high end. So I'm going to go back to that slide where we talked about that box plot. So here we go. So anything above 87.5. So it would be right here. So these two data values are outliers. So there's an outlier at 110, so I'm going to put an asterisk instead, and there's an outlier at 105. And the last data point that does not have an outlier is 75, so 75 would be here. So that side of the box plot would be modified. This would be our box and whisker plot here. The box and whisker would end here, but then we would have these two asterisks to denote that we had these two outliers. So these two crazy people who've been waiting in line forever to get on that ride. I don't know anybody who's that fanatical about rides, but you might. Anyway, so that is our modified box plot. All right, so please go and practice those box plots and finding those z-scores and those percentiles and those quartiles. And I will see you in the next lesson.